Okay, so different optical instruments make use of these same ideas. We look at the same kinds of things, like where does the image form, what is the magnification, except things like microscopes and telescopes, they don't care about things like about lateral magnification, where we talked about last time with M1 M is minus S prime over S. And this is actually the wrong equation number. We're looking in chapter 19 here. So for a microscope, it's 19.8 is the equation for total magnification, is 19.8, because it's a combination of the magnification of the objective and the eyepiece. Normally, when you buy things like microscopes or telescopes or eyepieces for those things, or binoculars, they'll talk about angular magnification instead of lateral magnification, where angular magnification is, if you look at something, you think about the angle that it takes up on a surface area versus what it looks like when you look in the eyepiece. It's very similar to lateral magnification, but it doesn't have anything to do, it's more generic than lateral magnification, because it's less about where the object is and what magnification you'll get. It's sort of everything's going to be twice as big or 5 times as big or whatever. So what all eyepieces do is they try to form that virtual image to get maximum magnification, and so that's at the near point. That's as close to your eye as they can get it. But that's why you have that adjustable eyepiece. So if you're a little older and you need to adjust where the image is at, you can do that. But all magnifiers, they try to form an image at the near point of your eye so that you get that maximum magnification. Now with telescopes, you still have a multiple system, but sometimes you have 2 lenses and sometimes you have a mirror and a lens. And there's advantages of one over the other. In the case of having the lens objective, we call that a refracting telescope because it refracts the light with the objective. In the case of the mirror, we call that a reflecting telescope because the objective reflects the light. Now, there are various advantages to the reflector over the refractor, but both of them are trying to form an image, and in this case, it shows it with an eyepiece. So the eyepiece in both cases would still act as a magnifier. You could use the same eyepiece on either one, it doesn't care. But it works like a magnifier again. It works like the same idea as a microscope, but much bigger. The magnification for it is given by equation 19.9. Okay, equation 19.9. Now, the idea with a telescope is you want to gather as much light as possible because we're looking at things that are usually very far away, so they're dim. All right. With a microscope, you're looking at things that are hard to see because they're tiny. And with a telescope, you're looking at things that are hard to see because they're tiny because they're far away. Okay, so in both cases, they're looking at tiny things, but one's tiny because it is tiny and the other thing's tiny because it's a way off. Okay, but in either case, you're trying to kind of do the same thing. Now, when you talk about telescopes, one of the issues, and you can even see this in microscopes too, you have some issues like chromatic aberration. If you use a lens objective, no matter what it is, a microscope or a telescope or even a camera can do this. We talked about how the index of refraction could be wavelength dependent. We talked about because the light actually went into the material, if the different colors were affected differently, then what that would do is that would spread the light out. That would take the light, and maybe red light bends less than blue light. And so what you get is you take white light coming from something, and when it passes through the lens or mirror, it spreads into the different colors like a prism would do. That's called dispersion when that happens. We talked about that with total internal reflection the other day. So what happens is if you have a lens objective, you can get a phenomenon called chromatic aberration where the image is blurry and it looks like it has multicolored halos around it. And that's not good if you're trying to look at detail on something that's small, you know, an image that's small. So the advantage, let's say in a telescope, of using a mirror is a mirror doesn't have chromatic aberration because the light doesn't go into the mirror, it just bounces off of it, okay? Both of them have a similar problem when it comes to spherical aberration. Spherical aberration is where you have a part of a sphere. If you've ever taken a class where they talked about conic sections and you took a section of a sphere, that's the shape of the mirror, or the shape of the lens is part of a sphere. If you use that shape, what can happen is stuff around the edges doesn't quite focus with everything else, and you get this blurry image again. So it's aberration or blurriness due to the shape. So it's spherical aberration. The larger the lens or mirror is, the more problematic this becomes. So we have to think about that when we build these big telescopes that have 10-meter mirrors. You know, so that's a consideration. Now, we haven't talked about physical optics yet, but one of the things that we'll see is something called resolution. And resolution is how you resolve detail. And you know about resolution even if you don't realize it, if you've ever looked at an airplane. So when you watch an airplane flying along in the sky, when it's way out there, you just see one black light moving, right? You just see that one light going along. But you know that there's more than one light on that airplane, because when it gets closer to you, you can start making out individual lights. So resolution is being able to resolve those kinds of details in objects. So what happens is there's something called Raleigh's criterion or Rayleigh's criterion, and they talk about that in starting on page 678, where they talk about the resolution and the wave nature of light. They talk about the resolution for a telescope and a microscope. There is a limit to how much detail you can see, and it has to do with what the angle of separation is. So the higher the resolution, the smaller that angle is that you can have and still see detail. So what happens is you're looking at essentially their diffraction patterns. If their diffraction patterns overlap, they are unresolved. You cannot see individual details. So when that plane is really far away, you just see one blob of light. As it gets closer, if you could watch it, that blob of light will start to come apart and you'll see like an elongated shape, and then eventually it'll be like individual lights. So you're going from unresolvable to resolvable, and that's because your eye has a diffraction limit. It has a resolution limit because of the structure of your eye, of how far apart those lights can be, and you still see them as two individual lights. That's fixed by biology. When I build a telescope or a microscope, I can determine that too, and that's something called the numerical aperture. And they talk about in that section 19.7 on the resolution of optical instruments. We're not going to do a lot of mathematics with that, but I want you to be aware of it because it is an important issue when you're talking about telescopes and microscopes. So this is what it would look like. This picture, oops, where'd it go? Go back. This picture is when it's unresolved. That just looks like a big blob of light. As it gets closer to you, you can start to see that there's probably two there because there's kind of a dent in between. It kind of reminds me of a cell undergoing that, what's it called, mitosis when they split. Okay, and then eventually what happens is you get them far enough apart that you can see them as two distinct entities. So that's resolved. So that angle is based on Raleigh's criterion. So actually, the closer they can be, and you still make them out as two, so that angle gets smaller as the resolution goes up, and the resolution improves. Okay, so that is all of that I wanted to share today.